Okay, so this is the MITACS video. We'll all be showing not just the simulation by itself, but how to make one. I hope it's not too long. I believe it's quite fast how you can make it. So I'll be starting in this video with the Fluent simulation, like the simulation of an airfoil, how to make one. Well, how I make these simulations. I'll be starting with obtaining the air profile. It's quite easy. You just visit this page and you go to the airfoil plotter. This is when you can choose. It's quite useful because you can choose from a lot of airfoil models. This one is just an ACA example. Just put the parameters you need, and you download a CBF file of coordinates. You can choose the code line. I was using 1000 millimeters, and when you download one, you see it's going to be like this. What I want now is just this airfoil surface. Okay, it's 200 points. You just pick these points and you have to put them in certain format, which is this format. You have the group point, X coordinate, Y coordinate, and Z coordinate. I'm gonna save this. It has to be in a block. So, okay. It's gonna be, well, in Spanish, it's this one, but I mean, in English, it should be like a text delimited by tabulation. It's gonna be test. So now we have the airfoil chord line. Now in our ANSYS, we're going to create a new one, which is just going to be Fluent Flow, Fluent. I believe this is just a little bit mixed up with Fluent and static, but I just made it because as I was working, I was just adding what was necessary. We're going to start the geometry in Design Modeler. Oh. It's not Space Beam, it's Design Modeler. As you can see, I define here like which simulation this corresponds to. This is the profile FX 67 at 0 degrees. Then I made one at 10 degrees, 20 degrees. I mean, if this is a NACA 2409, this is NACA 2412. This is just like the Fluent Flow, just airfoil profiles, and the static structural is just like prototypes, such as like prototype number 1, number 3, number 4. Okay, so now in Design Modeler, we have to change the units because we were working millimeters. The first, we select the XY plane. We're going to create a curve. Now it's what I was doing before. I was preparing the coordinates. I believe they are in here. Test, choose it, and we generate. Let's see. Okay, there it is. So now we have the profile. We're going to generate now a surface. I just selecting the edge, apply, generate again. And now we're gonna define the outside boundaries, like the air boundary. So for this, just gonna create a new sketch. Here in sketching, we're just gonna define a line, a vertical line. and like like a box, which is going to be like the air, like the air boundary. And we're going to choose the arc by 3 points, like an arc. Okay, this is just like a rough sketch to set up now the dimensions. Oh, but let's just make a constraint of symmetry to define like same distance from the surface, the center, the surface. Oh, I believe I did it wrong. It's going to be from the center. It's going to be the same distance between this and this point. Oh. I believe I'm not doing it right. Let's just undo this. Symmetry from the center, these 2 points. Okay, I believe that's it. Now let's just go for dimensions. This line, like this is a reference line to be able to put a mesh, a well-defined mesh. So let's just put it at 1/3 of the airfoil, which is like 33. Now this is going to be a 1,000. I mean 10,000 because it's 10 times the length of the airfoil, and this will also be 10 times the length of the airfoil. That's it. It's going to be like the air is going to come through this boundary and it's going to leave at this other boundary. These dimensions, I took them from a video, I believe, which I'm referencing the document. So you want to more clear about why these dimensions are there. There's the place to show it. So let's just delete these reference lines, and that's it. We're gonna now this is going to be a 2D model. I'm just going to create another surface from these edges. I believe I made a mistake. This is not surface from edges. It's supposed to be surface from sketches. Sketch. That's it. And for the next part, we're just going to need one solid, which is like an operation, a simple operation. I'm going to subtract the inner surface from the outer surface. So instead of unite, we're just going to put subtract. This is going to be your main model. And to select this, if you click, I mean, I'm still selecting the big surface, so I'm just going to change it. Select apply. Okay. And when you generate it, you can see that it's just the big surface. It's not the same as the small surface. There's like a new select surface, in which is just the big one without the smaller one. Now I'm just gonna create some lines of reference. We're just gonna generate another sketch, a different one, to be able to generate a well-defined mesh. Just some lines as this. Here, a point from the center. And there's some trouble with doing this. I will just put a line in here. And since I know the airfoil is just 1,000 millimeters, you're going to put in here 1,000 millimeters. If you don't do this, you will have trouble in making the next few steps. So just put the final line here. I hope it's well defined, because if not, I'm gonna have trouble. And then I'm just gonna extend these lines so they touch, like they go to the limits. Oh. You see now that it's just well defined lines. With this line, I'm just gonna create new lines from sketches. You're gonna select all the lines, holding Control, and we generate. You can see that these are defined, but somehow these are not. So let's just create another one. These two. What is this? So, this one, I hope they do get defined. Okay, so we got the one that's missing. I believe this is counted as just a single line. I don't know why. I mean, yes, as you know, this is well defined. And the final step is just to create a projection. So the below surface is defined by these lines. So just select all lines again. Select the touches, which is the behind surface, reapply, and generate to the final. Okay. The design model process is finished. We're going to start now with the mesh. Okay, so going back to the mesh, we have opened this fluid flow, which is like the mechanical ANSYS. Here we have the airfoil and with the boundaries. We have to check this coincide. I believe they do. When selecting edges, yes, I mean they're separated, because if they are not the same, we're gonna have some problems. Okay, this I believe will be fine. Let's just suppress the line body, so we select this instead of the projection we just made. Okay, so when making the mesh, we're gonna insert some sizing. This to just have it like really well defined. Okay, so in the first one, we're gonna select the same length edges. Well, they're not quite the same length, but almost the same. We apply to it. We define it by number of divisions. What we're gonna do is we're gonna have divided this, I believe, 200. Okay. And for the behavior, we can just put the bias. So it, I'm gonna show. We're gonna see like a preview from it. Yeah, I believe it's 5,000. It doesn't quite show, but what this does, it's thinner the closest to the airfoil. So when we're gonna see the results, they're gonna be like well defined. I believe this is what needs to be made to have a quite defined mesh. So I'm just gonna select this edge to be reverse biased. So and that is correct. Just keep it like this. See how it goes. Now we're gonna select these three edges, which are the same size. Again, we're just gonna do number of divisions. This is gonna be 100. We're gonna put some bias as well. To 500. Like this, yes. That's good. And we see the orientation, it's correct. So we don't have to put a reversal. You can see the divisions are bigger. The part where you go from the airfoils, and that's what we want in this case. Okay, just another sizing. We are missing this. We hold Control and we select these edges about the same size. Number of divisions. This is just going to be 50, I believe. This is, and there's no bias in here. You're just going to have let's go by, and let's select and we add one for the final edges. This surface, this surface. Again, number of divisions, only 50. Oh, I'm sorry. It's going to be. No, we have 4 edges. There we go. We finally insert a face mesh. This is so the software can mesh each one of the faces. There's enough the mesh. Just generate it to see how it looks. Oh, it doesn't take that long. Okay, I pause the video and start recording again. We see a well-defined mesh. In this case, we're happy with the mesh. As you see, it has, the closer you get to the airfoil, the smaller the mesh sizing gets. And we can see it's quite fine. Now, before going to the next part, we're gonna create name selections here. So when we open ANSYS Fluent, we can decide this is the air. I'm just gonna put air fluid. Use air fluid. We're just gonna now, so we can see how it is. So select this now. Okay, create new selection. This is gonna be the airfoil. I'm gonna put wall, so it recognizes a wall. All of these edges. Gonna be the inlet, and use the final 2 edges. Gonna be the outlet. Okay, so let's just check if everything is correct. Air fluid, the wall, air for wall, inlet, okay, outlet. Okay. So let's go now to the workbench. I believe we need to make this. You can see here how the process is going, updating. Okay, let's go. And let's go to ANSYS Fluent. Here we can see it's gonna start Fluent. And help. I'm gonna pause the video in case it takes long. Okay, so we have this. I believe you can put this to double precision. You're just gonna increase the precision of the results, but it takes too long if I put 2D1 because of my computer. So it's gonna start going like this. Okay, it's opening now. Let's just wait a little bit. This is some summary. How usually for way parallel execution. Okay, it's building the setup. Let's choose the viscous model, which is a bit, I believe, the more important. I believe the best one you can choose is this standard one. It's how the model is fixed. It's some equations to define the viscous fluid. And that's the only one we have on. All the others are off. You can check the fluid as air, density and viscosity. And the solid, well, in this simulation, there's actually not solid. So let's see the graphics. Oh, we can see how the inlet is defined, the outlet as well. So that's good. Let's just check the boundary conditions. Okay. So the inlet here we defined how the flow is going to go through the inlet. This time we're just going to put magnitude and direction. I choose, I believe it's 3000 Reynolds number, which is 43.9 meters per second. We can see that the flow direction is just the x direction. So these arrows are not quite okay. Like the fluid is just going to go towards the right of the. This doesn't actually show the airflow. Okay, so that's are we gonna change this time for the simulation? Now this is the important other aspect, which is going to be the force report of drag. We're going to rename this drag, which is again to define airfoil wall. It's a force vector in the x direction. Just going to do 10 times frequency. We're going to print it also. Okay, and again the same, but with lift. The lift of the airfoil wall. You can see that it's a force vector in the y direction, it's upwards. The drag was in the x direction, which is right to the right. So again, we're going to use the frequency to 10 and the print to console. Okay. The methods. Yes, this is correct. We were supposed to change this. Okay. No, it's in the, okay. In the wrong calculation. We're gonna do 500 iterations. It's suggested to do 1,000, but my computer is just really slow, so it takes too much. That's why we're gonna report the intervals each 10 iterations. This is all I can do. The other stuff, I'll just leave it the same, and let's just calculate. You're gonna ask to initialize the model. Yes, initialize it. And we're gonna roll the calculations. I'm just gonna show you how where the progress is going, and I'm gonna pause the video after that. It takes just like a couple minutes. Okay, here we can see it's gonna calculate the solution. And we see the iterations and the progress. So see 500 iterations and how the progress is going, and the plots, lift and drag. So I'm gonna just pause the video and resume it when this is done. Okay, so after remarks, I should have taken into consideration. We're gonna compute from the inlet. So we have the inlet value 43.9. So it calculates all the other aspects from here. Now here in monitors, I believe what we will also change is the residual. So it doesn't converge, because if I run it, well, I run it actually, and it converges really fast after 30 iterations. That's not what I want. I want to run like all the iterations. So I'm just put it here a really small value so it doesn't converge that fast. And we're gonna run the calculation again. This for current calculation, sure. Let's just wait until this is finished. Okay, so the calculation is finally complete. You can see now the 500 iterations, how it stabilizes around like, I'll say 350. It's on the same value. With the lift plot, it's like a similar plot. And how to know the exact value? We go here to people definitions. We pick these two, and we click compute. Then we go here to the console, and here we have the exact values. In this case, I believe it's just too slow because the wind speed is 43, barely makes any difference. Now the cutovers. We can go to cutovers in graphics. We select the pressure. There's actually plenty of, you can choose velocity or I don't know. Okay, well, pressure, let's go. And it's funny because you can see the pressure coefficient, dynamic, absolute, but at least I think these two are pretty close, the total and absolute pressure. Of course, there's a wide difference between them. Let's just choose the static pressure. Here we don't have to choose any of these. Just compute, the minimum and maximum value, and save and display. To go here to graphics and to see the. You can barely see this. It's just small. And you can make the zoom in. As said before, the maximum value is what produces like the drag effect, and the minimum value, it's like the difference in pressure. We can see there's a difference between the upper surface and the lower surface, and this is causing the lift. Okay, so this is how I got all the results on my report. I hope this video is not too long, and I'll make another video showcasing the static structure of ANSYS.